Have you ever wondered how planes fly? Why are sports cars designed with fancy spoilers on the back? It all comes down to the science of aerodynamics, and the physics behind it all can be explained with a simple frisbee. Along the way, we'll learn about the forces which enable things to fly, as well as the many challenges which oppose flight. At the end, we will have learned how a frisbee can be redesigned to fly farther using physics, what the most optimal throw is, and the frisbee's scientific connection to our daily lives. All on this episode of Flying Physics, where we dive into the physics of frisbees.
Well, first, what is a frisbee? Well, a frisbee is a circular disc that usually weighs around 175 grams, that has a thicker lip on the edge, and flat top and bottom. So, how does this piece of plastic fly? Well, let's get into it.
First, let's start out with why a frisbee shouldn't fly. Well, gravity. Practically, given that we are standing on the earth, everything will get pulled down towards the ground. So, how do we make a frisbee fly? Alright, well, let's take a look. Using free body diagrams, we know that in order for there to be a displacement upwards, there must be a greater force opposing the downwards force. What does that mean? The more force we throw it with, the farther we'll go, right? Well, not quite. As you can see, even though there's a lot of applied force, the frisbee goes nowhere. So how do we produce this upwards force? The answer to that? Lift. We can explain it using Newtonian forces. Lift is the force on any flying object that opposes the force of weight and gravity. Because of the frisbee's curved shape, it is able to generate lift and glide flat through the air. This force is perpendicular to the airflow. As the frisbee travels forwards, the air underneath it is being pushed downwards. According to Newton's third law, where every force has an equal and opposite reaction, the air pushes back up on the frisbee. That's how the frisbee will fly. However, why does the air push it upwards?
The Coanda effect and Bernoulli's principle can be used to explain it. But first, to understand these concepts, we must understand air pressure. Air is made up of several invisible gases that all have a mass. This mass is made up of molecules that move in rapid random motion. This motion causes a force called air pressure.
As the frisbee travels, the gas particles that are floating around will follow the curvature of the frisbee. This is called the Coanda effect. It can be demonstrated with running tap water and a plastic spoon. In this case, the water is the gas in the air and the spoon is the frisbee. As you can see, the water particles follow the path of the spoon, even sticking to it. The Coanda effect can be seen popularly in daily life, such as in Dyson's new hair curler, and is also the reason why your drink might just not quite make it into your cup.
Next, Bernoulli's principle. A scientist named Daniel Bernoulli found that when a gas, like air, moves, it'll exert less pressure. This is because the air particles will be farther apart when they're moving. So, his principle states that the faster the air particle's velocity, the lower the air pressure will be. Similarly, from the frame of reference of an air particle, the faster an object moves through the air, the greater the imbalance of air pressure, thus leading to a greater lift force.
This can be demonstrated by a ping pong ball and a hairdryer. As you can see, the ball will stay in the air when the hairdryer is on. When the hairdryer is tilted to either side, the ping pong ball will still remain in the air, even though it looks like it should fall. This is because the air from the hairdryer is moving a lot faster than the surrounding air. This means that there is more pressure in the surrounding air and the air from the hairdryer has less pressure. This causes the ball to remain in place in the direction of the hairdryer.
We see this concept applied in almost all flying objects, UFOs, kites, and even birds. However, we see it most in aircraft. The shape of the aerofoil is different for every aircraft. It is designed to give the best trade-off between aerodynamic forces. On many airplanes, the bottom of the wing will curve downwards slightly instead of being flat. On other aircraft, such as gliders, it'll curve upwards. On a stunt plane, which is just as likely to fly upside down than it is the right way up, the curve on the bottom of the wing will always be the same as the top.
Now, we can apply these concepts to frisbees. Because of the curved shape of the frisbee, the air particles will follow its curvature. Additionally, the particles will accelerate faster over the top of the disc rather than the bottom. And as we know, faster airspeed means less air pressure. Due to the inequality of air pressure on either side, more force is applied to the bottom of the frisbee upwards. And there it is, that upward force. This is what allows a frisbee to fly.
Well, now that we know about lift, we should be able to throw a frisbee, right? Well, not quite. There's still one more component to a frisbee's flight.
The aerodynamic forces, including lift, are not centered. What this means is that lift on one side of the frisbee will be larger than the other side, creating a net torque. Torque is a measure of how much a force acting on an object causes that object to rotate. Once this torque is created, a stable flight is no longer possible as one side of the disc is popped up.
So, how do we fix this? Use the flick of the wrist. Adding spin to the frisbee will allow it to have its long, majestic flight. This is called gyroscopic stability.
If you get pushed while standing still, you move in the direction you were pushed. Similarly, when a frisbee is not spinning, it will move in the direction with less of a lift force. However, if you're already moving, the impulse you receive is added to your initial momentum to equal your final momentum. For a frisbee, we can treat your walking as its spin, and the added impulse as the imbalance of aerodynamic forces. This imbalance will affect the direction of the frisbee less than the first scenario. This applied force also determines your final direction. This is just like how a frisbee will almost always tilt and head in a non-straight direction.
This is because of the frisbee's angular momentum. With more spin comes more angular momentum. This momentum is reliant on two things: the frisbee's moment of inertia and angular velocity.
Moment of inertia is a scalar quantity where matter resists change in its state of spinning motion. This is dependent on many different factors, including the distribution of mass and the positioning of a rotational axis. A frisbee is strategically built so that most of the mass is on the outer edge and the rotational axis is almost perfectly centered. Angular velocity is the pace at which an object is spinning. The thrower is able to control this variable when a frisbee is thrown. Angular momentum is given by moment of inertia times angular velocity. However, we know that the moment of inertia will stay constant. This means that the velocity will change. The larger the velocity, the more angular momentum, and thus creating more spin, and ultimately a more stable flight.
If you're still confused about gyroscopic stability, think of it like this. When you're riding your bike, why aren't you able to remain upright when your wheels aren't turning? This is gyroscopic stability. The wheel's angular momentum is high, so it is easy for the bike to remain upright. It is also why football players would call a good throw one with nice spin, because it has a stable flight. It's also how figure skaters and dancers can spin for so long in one spot.
So, to conclude, we learned that lift and gyroscopic stability will work together in order for a frisbee to fly.
Aerodynamics is part of a broader science known as fluid dynamics. Fluids include liquids such as water as well as gases such as air. Dynamic pressure simply refers to a fluid in motion and the pressure associated with said motion. This is described by the equation Q equals 1/2 rho V squared, where Q equals dynamic pressure, the Greek letter rho equals the density of the fluid, and V equals the velocity of the fluid. Since the density of a given fluid is relatively constant, the value of Q, dynamic pressure, changes mainly dependent on the velocity of the fluid. If you place an object in the fluid's path, it experiences an applied force directly proportional to the dynamic pressure and the frontal area. In other words, if you wish to increase the applied force, you can increase the dynamic pressure, most simply done by increasing the speed of the fluid, or the surface of the object. Dynamic pressure is directly connected to drag. Drag is a force that resists the motion of an object through a fluid, and it acts in the same direction as the flow of the fluid. Since we're looking at flying objects, our fluid will be air. In this case, you can think of drag as friction in the air, or air resistance. The formula for drag is very simple. D equals Q times A times C subscript D, where D equals drag, Q is our dynamic pressure from before, A is the frontal area of the object, and C subscript D is the drag coefficient for that shape. A drag force is inevitable on any moving object. We know this because looking at the equation, none of the variables can equal 0. We can see this, but first we need to understand frames of reference. A frame of reference is a perspective from which motion is described or observed. We can view dynamic pressure from two reference frames. Firstly, we can visualize an object at rest with fluid in motion. Conversely, we can visualize the object in motion through the fluid at rest.
In terms of drag, we can use these reference frames to realize that the dynamic pressure can only be zero if the object and the fluid are both at rest. In regards to the other two variables, the frontal area of an object cannot be zero, as this means the object doesn't exist, and the same can be said for the drag coefficient. So how can we make the Frisbee go farther? Although drag is inevitable, we still wish to minimize it as much as possible so the Frisbee can travel as far as possible. Taking a look at each of the variables at play, we can begin to deduce a method by which we can reduce aerodynamic drag. Intuitively, an object traveling through the air slowly will experience less drag than one moving at high velocities. We know this is true as from the reference frame of a still object, this means that the air isn't pushing as hard on the object. However, we can't just throw our Frisbee at slow velocities, as it won't generate adequate lift force to fly. Additionally, we want to optimize our Frisbee for a wide range of velocities, so we do not want to limit it to slow speeds. There are really two ways to reduce aerodynamic drag: make an object thinner and/or make it more streamlined, consequently reducing the frontal area and the drag coefficient respectively. Let's start by making it thinner. The Frisbee is approximately 3 centimeters thick, but what if we squashed it down to just a few millimeters? When the disc is thrown without any spin, the front flips up and the disc spins in this backwards manner to the ground. This flight is unstable, but what can we learn from it to enhance our Frisbee? Before we can answer this question, we need to learn something about the center of mass and center of pressure. Firstly, the center of mass is an imaginary point where the mass of an object is assumed to be concentrated. In other words, it is the average location of the weight on the object. For this reason, it is also called the center of gravity, because the force of gravity can be drawn directly down from that point. Similarly, the center of pressure is another imaginary point where the pressure on an object is assumed to be concentrated. In other words, it is the average location of pressure on the object. Just like center of mass, the center of pressure also goes by another name, the center of lift, as this is where the lift force can be visualized from. On a typical airfoil, the center of mass and center of pressure lie around the quarter chord point, 1/4 of the leading edge of the airfoil. Their exact position in relation to each other are important for stable flight. The center of mass on fixed objects is constant. However, the center of pressure differs with the angle of attack, moving forwards with increased angle and rearwards with decreased angle. Now we are ready to answer our original question. What can we learn from this unstable flight? We can see in the first flight that the front of the disc pops up early in the throw. This shows us that the lift force is towards the front. We also know that this is true because of the typical location of the center of pressure or center of lift on an airfoil. From this, we know that when the disc is thrown, it will experience a lift force near the front. So how can we stabilize it? Earlier, we learned that spin can help stabilize the flight of a disc. So let's try adding some spin to the throw. With the spin, the disc still does not fly well because of an effect known as gyroscopic precession. Gyroscopic precession is a phenomenon that, simply put, states that if an object is spinning and a force tries to tilt the axis on which it is spinning, it will respond a quarter of a revolution later. You'll notice that when I throw the disc with clockwise spin, it banks to the left, and it will do this every time. This is due to the lift force being at the front, and because of gyroscopic precession, the disc responds a quarter of a revolution later, pushing the right side up. The same is true as if I were to throw the disc with counterclockwise spin, except it would bank to the right instead. So what can we learn from this throw? Well, the spin didn't help stabilize the disc, so what's the issue? We can now see that it is crucial for us to center the lift force on the object. Frisbees do a great job of this with their curved edges. However, this adds significant drag to its flight. So how else can we center the lift force? Let me introduce you to the aerobie. The aerobie is a ring-shaped flying disc. Its ring design comes from trying to center the lift force on the object. If half of the lift force is at the front and half is at the rear, the sum of the two halves would be positioned fairly close to the center of the object. However, the lift forces are actually not balanced due to what's known as downwash. Air that passes over an airfoil is deflected downwards as a result of the production of lift. This deflection is known as downwash. In the case of the aerobie, the lift produced by the front half of the ring would downwash the air behind it. As a result, the air striking the rear half of the wing would be at a lesser angle, or if we change our frame of reference, as if the rear half is flying with a negative angle of attack. Ultimately, this means the front half would produce more lift than the rear half, causing the lift force not to be centered on the aerobie. So how do we counteract this? The aerobie has two intentional design features that help it center the lift force. It does this by decreasing the lift force produced by the front half so it matches the rear half. The first feature is a slight conical design. This conical design angles the front half slightly downwards and the rear half slightly upwards, causing the front half to produce less lift. However, it still doesn't match the rear half. Now enter the second feature, a special outer rim which adjusts how the air interacts with the ring. When air strikes the outer rim, it is separated from the airfoil, which reduces the lift of the front half. Then, when air flows over the rear half, the rim at the end has very little effect on the produced lift force. These two features adequately decrease the lift generated from the front half, allowing the sum of the two halves to be well centered within the aerobie. All in all, the aerobie design allows it to fly stably and much farther than a traditional frisbee due to its thin, streamlined design and balanced lift forces.
So, throughout this process, we analyzed an aerobie and a frisbee. Now that we know all of the concepts and mechanics, what sets them apart? Lift. One of the most evident differences between the two is that there is a gaping hole in the aerobie, while the frisbee is more disc-like. This has a huge impact on producing lift. Since an aerobie won't have a surface to push air downwards, it is unable to generate as much lift as a frisbee can. We know this because when we tried to air bounce both by throwing them downwards, the frisbee launched high into the air while the aerobie just simply glided across the air. Second is drag. Because of the aerobie's slim and lightweight design, it is practically slicing through the air with minimal drag. Compared to the frisbee where the rim is thick, the frisbee definitely experiences more air resistance during flight. However, the frisbee will be more stable in flight as it is easier to balance a larger mass. This brings us to our third topic, mass. The aerobie was designed to be lightweight and easier to throw, and indeed it is. The aerobie is able to travel farther distances than the frisbee with the same amount of force. The farthest recorded throws are 406 meters for the aerobie and 338 meters for the frisbee. This gives the aerobie an approximately 70 meter greater range than the frisbee. This brings us to the pictures on the screen. Each picture represents the farthest we were able to throw each disc. The left is the farthest we could throw the aerobie, and in the red circle you can see I'm almost invisible to the camera, and on the right side is the farthest we were able to throw the frisbee, and obviously I am a little closer to the camera, hence why I'm more visible.
With all these differences, we concluded that it would depend on the circumstances and what one would classify as the perfect throw. With many debates, we decided to study the optimal angle of attack. For this experiment, we considered the farthest distance to be our independent variable. The optimal launch angle will be the angle in which the frisbee or aerobie traveled the farthest. We recorded distances for 10 different angles for both the frisbee and aerobie. In total, we conducted about 200 trials. It took a while. There were various factors that we considered. These included strength of throw, wind, spin, and measurement uncertainties. Here's what we found. We found that in general, the aerobie flew farther than the frisbee. This makes sense as we know that the aerobies are designed to fly farther. Furthermore, in this case, the frisbee's ability to generate lift will not help and create more torque and turbulence, causing its flight to actually be shorter. In this case, the spin was kept constant at a minimal amount. Without spin, the frisbee is a lot less stable. This is why our findings, considering all factors, make sense. As for the angle of attack, we found that the optimal angle was 40 degrees for both the frisbee and aerobie. Since this angle is the one that produces the farthest throws, we can assume that this angle is where lift and drag are the most balanced. Overall, we can conclude that it cannot be said which flying object is more superior than the other. It all depends on the context of what your perfect throw is and what external conditions may be considered.
With all of the new concepts we have learned about these flying objects, we can apply these concepts to many other things in daily life. It is most evident in an aircraft, where a frisbee is similar to the wings of the plane, in both shape and lift. Lift can also be applied to race cars. Since race cars move so quickly, spoilers on the rear actually help them to stop from lifting. They're designed to counteract the lift. The air will push the car down rather than up. With that being said, that concludes our video. We hope you learned a lot and that this piqued your interest in a soaring science. If you still want to learn more, you can visit our website linked in the description below.